Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will look at terminated transmission lines, introducing you to the concepts of reflection and transmission coefficients. Now, before doing that, let us actually set up the problem that we are about to investigate. So far in the previous modules, we considered that the transmission lines actually had no end. There was no load on the transmission line, right? There was no source, there was no load that we considered. So, magically voltages were appearing on the transmission line, both going along positive or negative z axis. Now, suppose I consider a semi-infinite line, that is, I consider that the source is located far away from the transmission line, but I have a load situated here. Here in my language means z equal to 0. Okay. So, this is a coordinate system that is typically used when dealing with transmission lines, that loads are located at z equal to 0 and sources are located at some z equal to minus some value. Okay. So, for us z equal to minus infinity is the source initially, but we will relax that assumption later on. Okay. So, what we are actually looking at is what happens to these waves, okay, when you terminate the transmission line with a load. Okay. Let us look at that one. Look at the way I have drawn the transmission line. The transmission line is indicated by these two lines which I have drawn. Okay. I have also drawn two small sinusoidal kind of a thing to indicate that we are considering a frequency domain behavior, and I have a wave which is going in the positive z axis as well as in the negative z axis. I also locate the load at z equal to 0. So, this is the load that we have kept. It could be a antenna, or it could be a television set, it could be anything that you are considering as a load. In a high speed digital system, this could be a address bus on one hand and the module that the address bus is actually addressing to. So, it could be any kind of a thing, and this load could also be frequency dependent, meaning that there could be some inductance or capacitance in this particular load, so that the impedance is what you would want to consider, not just a load resistance. So, you actually are considering a slightly complicated case of load impedance. Okay. The load impedance of course is the termination condition, which tells you that there will be some current flowing through the load, which we can label as IL, and there will be certain voltage across this load which we can label as VL. Okay. Now, on the transmission line at any z that I can take off at any point on the transmission line, there will be both positive and negative going voltages, right. So, the total voltage here in terms of the phasor that I would have is given by V0 plus e power minus j beta z plus V0 minus e to the power j beta z. So, the V0 plus wave or the positive z travelling wave will be going along the plus z direction, and this V0 minus e power j beta z will be going along minus z direction. Okay. That would be the same case if I draw the plane here. At this plane also it would be the same situation, this plane it is also the same situation, it would exactly be the same situation at z equal to 0. But what will happen to this V at z equal to 0? This would be equal to V0 plus V0 minus, that is the total voltage, right. That would be equal to V0 plus V0 minus, simply because z is equal to 0 here. But at this voltage, I do know that the total voltage is actually the load voltage VL. By the way, I have used a very kind of a irregular shape of wires to connect this ZL load, right. The reason what I have done is to show that anything beyond this region where the load is connected, the spatial extent of this load can be neglected. In other words, this region what we are considering is the lumped region, this is the transmission line region. Okay. If this length of this region that I have considered, or the shape of this region that I have considered, has no bearing whatsoever for the relationship between voltages and currents. So, to come back, at the load voltage is VL and the load current is IL, and the load voltage here appear from the left, if you approach the load, will be given by V0 plus V0 minus, which would then be equal to VL. Okay. This is fairly simple, because the voltages, if they are different, then there has to be some other element which is actually taking up that extra voltage, and unfortunately that cannot happen here. You can also confirm this one by applying a simple KVL around the loop. Near the load, if you apply KVL, you will see that from the left the voltage will be V0 plus V0 minus, and on the right hand side it would be VL, and those two voltages are the same. Similarly, the currents must also be the same. In one of the exercises you must have derived what is the current phasor, and the current phasor is given by I0 plus e to the power minus j beta z plus I0 minus e power plus j beta z. You must also have derived I0 plus and I0 minus to be V0 plus by Z naught and minus V0 minus by Z naught, with these phase factors going to 1 here because we are considering at Z equal to 0. So, the current phasor at Z equal to 0, which will give you the total current on the transmission line as the current approaches the load, will be given by V0 plus by Z0 minus V0 minus by Z0, which will be equal to the load current IL. Okay. The load current can also be written as VL divided by ZL, because IL must be equal to VL by ZL. Now you have two equations. Okay. One equation telling you that V0 plus V0 minus is equal to VL, and you have another equation which tells you that V0 plus by Z0 into V0 minus by Z0 must be equal to VL by ZL. From these two you can actually reduce one of the constants. You can show that, or you can write this one as V0 plus V0 minus is equal to VL, V0 plus minus V0 minus is equal to Z0 by ZL into VL. I take V0 plus as a common factor out, and what I get here is 1 plus V0 minus by V0 plus, that would be equal to VL. In the next equation, if I take this fellow common, I get 1 minus V0 minus by V0 plus, this would be equal to Z0 by ZL into VL. Okay. I can now divide this equation by this equation, and also before doing that, let me denote the ratio of the amplitudes V0 minus to V0 plus. Remember, V0 minus is the wave which is getting reflected, or wave which is actually travelling along the minus z direction. V0 plus is the wave which is travelling along the plus z direction. The ratio of these voltages V0 minus and V0 plus, which represents the incident and the reflected voltages. Incident voltage is V0 plus, the reflected voltage which originates from the load and travels along the transmission line in the direction opposite to the incident voltage is called as the reflected voltage. Whenever the load ZL will not be equal to the characteristic impedance of the transmission line Z0, there will always be voltage reflections. Okay. Otherwise your KVL, KCL won't be satisfied at the load. Okay. So, the reflected voltages are created necessarily as the mismatch between the load and the characteristic impedance, as we will also see later on. Okay. So, this equation can be simplified to write V0 plus 1 plus gamma L is equal to VL. Okay, where gamma L is the load reflection coefficient. So, this amount of reflected amplitude to the incident amplitude is called as the load reflection coefficient. Okay, and this load reflection coefficient at the load point, reflection coefficient at the load is denoted by gamma L, and that is what I have used in this expression. Okay, in this expression I have used that one. I can simplify the second equation by writing this as V0 plus 1 minus gamma L. This would be equal to Z0 by ZL into VL. Now I divide these two equations. Okay. When I divide these two equations, from the V0 plus will go away, VL will also go away from the equations, and what you get is 1 plus gamma L by 1 minus gamma L is equal to ZL by Z0. Right. So, when I divide the second equation from the first equation, right, I can rearrange this equation to solve for gamma L. I will leave this as a simple exercise to you. So, let me also mention that this is an exercise that you can easily do. Okay. Invert the relationship to show that the load reflection coefficient gamma L is given by ZL minus Z0 by ZL plus Z0. Okay. Please remember, reflection coefficient tells you the ratio of the reflected wave to the incident wave. If gamma L is equal to 0, the voltage that is getting reflected will have an amplitude of 0, which means that there is no reflection. So, gamma L equal to 0 indicates no reflection. What is the nature of this gamma L? Well, we just said that ZL may be complex, correct, because there could be some inductance and capacitance in the load. If ZL is purely a resistor, then the reflection coefficient will always be real. Assuming that Z0 is real, we will assume that Z0 is always real. So, in that case the reflection coefficient will be purely real, otherwise it will in general be complex. Any complex number can be represented by its magnitude as well as its angle, okay, which we can write in terms of the magnitude and the phase angle. We can write gamma L, which may be complex because ZL is complex, can be written in terms of its magnitude and a certain phase angle phi L. Okay. Now, once I know that this is the load reflection coefficient, I can write down my total V of Z as V0 plus e power minus j beta z, which is really the wave which is propagating along the plus z direction, plus V0 minus e power minus j beta z, but e power plus j beta z, but V0 minus can be written as gamma L into V0 plus, correct, because the ratio of reflected to incident is the reflection coefficient voltage and this wave is propagating along minus z direction. I can simplify and write this as V0 plus e power minus j beta z, which I can remove outside, take it as a common factor, then I get 1 plus gamma L e to the power j 2 beta into z. Further, I can denote this gamma L into e power j 2 beta z as gamma L of z, which will tell me how the reflection coefficient is varying at different points on the transmission line. So, this is at the load point where z is equal to 0, and at different points the value of gamma L will be changing. To this gamma L, if you add by 1 and multiply by V0 plus e power minus j beta z, you will get the voltage phasor, the total voltage on the transmission line. Now, how do I obtain the voltage as a function of z and t from the phasor? Okay, in order to do that one, you simply multiply the phasor by e power j omega t factor. Remember, this is the factor that you have dropped earlier to go from z and t notation to the phasor notation. Now, you insert this e power j omega t and then take the real part of it. Okay, so this is how you go from one domain to the other domain. Okay. Now, let us look at several different cases for gamma L. Let us consider the case where ZL is equal to infinity. When will I have ZL equal to infinity? When current is equal to 0, the load current is equal to 0 and the load voltage is some number greater than 0, right. That is to say that I have no current flowing through that load terminals and the voltage is some value, right. This is clearly the case of an open circuit termination. So, an open circuit termination is simply the case where the transmission line ends are just left as it is. What should be the total voltage at any point z along the transmission line? Well, first find out what is the load reflection coefficient. What is the incident voltage? Incident voltage is V0 plus e power minus j beta z. At z equal to 0, the incident voltage will have an amplitude of V0 plus, but clearly this is the case where no current is flowing, right. So, what should happen to the voltage that is incident? Entire voltage has to reflect back. You can see that by going to the reflection coefficient expression, the load reflection coefficient expression, gamma L is given by ZL minus Z0 by ZL plus Z0, which clearly gives you plus 1. Okay. Gamma L of plus 1 means full reflection, and gamma L also turns out to be a real number here. And remember, what is gamma L? This is nothing but V0 minus by V0 plus, which implies that the reflected voltage amplitude is exactly equal to the incident voltage amplitude. Okay. Once that happens, you can write down the total voltage phasor at any point on the transmission line as V0 plus e power minus j beta z. I can take V0 plus as a common factor out and then write this as e power plus j beta z. I know that this is e power minus jx plus e power jx kind of a expression. So, this will give me 2 V0 plus cos beta into z. Okay. Now, let us actually try and plot this 2 V0 plus cos beta z, the magnitude of this one. Let us plot the magnitude of this voltage phasor. Okay. So, this is the point where z is equal to 0, z of course is increasing along this right hand side. Okay. How would this 2 V0 plus cos beta z magnitude look? initially it would be maximum here with a value of 2 V0 plus, and then it would go down to 0 at minus pi by 2 beta. Why would it go to 0 at minus pi by 2 beta? Because cos of beta into some value of z must be equal to pi by 2 for this fellow to go to 0, and remember that z is negative as you go along the transmission line. Therefore, this would be 0 at minus pi by 2 beta. Thereafter again it would be maximum, it would be minimum, it would be maximum, and it would go on like this. What would happen to the current? Well, we know that current has to start at 0 here because there is no current flowing in the open circuit region, but then the current will reach its maximum at the same time where the voltage is reaching its minimum, and then it would be out of phase with respect to the voltage by about 90 degrees. So, this is the current waveform and this is the voltage waveform that you would see on a terminated transmission line when the termination happens to be a open circuit. Okay. Now, this is the voltage phasor. What would be the voltage, actual voltage as a function of z and t? Well, let us look at that one. All I need to do is to take this phasor and multiply this phasor by e power j omega t and then take the real part of it, right, in order to obtain the voltage as a function of z and t. And when I do that, what do I get? I get 2 V0 plus cos beta into z, right, times cos omega t. Okay. If you now go back to the transmission line and pick a point where cos beta z is equal to 0, right, that is the case where we had considered at minus pi by 2 beta. If you pick z is equal to minus pi by 2 beta point, you would see that no matter what time is changing, the voltage at this point will always be at 0, right. Similarly, the voltage would always be at 0 at after a pi value here, when this will be at minus 3 pi by 2 beta. So, these locations where the voltage is 0 is not changing, they are always present no matter what time is changing. Okay. We will contrast this case with a travelling wave in a very short way. This wave in particular, where in this wave in a situation where this maxima or the minima is not changing with respect to time and hence kind of nothing is moving, is called as a standing wave. Okay. This is called as a standing wave. Alright, let us consider the second case. I consider ZL is equal to 0, which happens to be the short circuit condition. In the short circuit case, I know that the voltage would actually drop down to 0 and the current would actually be maximum there. Okay. But what would be my load reflection coefficient here? Gamma L will be equal to minus 1, right. Because gamma L happens to be minus 1 in this case, the total voltage phasor V of z that I get will be of the form V0 plus e power minus j beta z minus e to the power j beta z, or simplifying by utilizing the relationship of trigonometric and complex exponential, this would be minus 2j V0 plus sin beta z. And again, if I plot the magnitude of this, I see that the voltage would have dropped to, sorry, this is a short circuit, right. So, I have to indicate that this is a short circuit, I have indicated that here. And when I look at what would happen to the magnitude of the voltage here, it would be 0 and then it would reach to its maximum at a later time and then again go down to 0. Where would I get a maximum? I would get a maximum at minus pi by 2 beta. This number minus pi by 2 beta is coming up again. This is the location of the first maximum when I terminate the transmission line with a short circuit. Previously, this was the location of the first minima when I had terminated the transmission line with a open circuit. I will leave this as an exercise for you to find out what is the voltage V of ZT. Okay. From the phasor you should be able to find out what is V of ZT and also locate and find out whether you get a standing wave or you will get a travelling wave as a result of this. What is the travelling wave? Let me go back to the situation where I consider ZL is equal to Z0. Okay, this is a very special case of termination where the load is terminated in the characteristic impedance of the transmission line. When I do that, what will happen to gamma L? Well, gamma L is ZL minus Z0. Since ZL is equal to Z0, gamma L will be equal to 0. Since gamma L is equal to 0, this is the third case we are considering. So, gamma L equal to 0 simply implies V0 minus is equal to 0, which means there is absolutely no reflected wave, and the voltage phasor is given by V0 plus e power minus j beta z. If I plot the magnitude, what would happen? This is something that is interesting. So, now again I am going to terminate this one by Z0, right, as I terminated here, and if you look at what is happening to the magnitude will be a constant V0 plus. That is kind of surprising. That is surprising only because you go back to what is V of Zt for this case. Voltage as a function of both Z and T will be given by V0 plus e power minus j beta z multiplied by e power j omega t, and then take the real part of it. What you get is V0 plus cos omega t minus beta z. Where is the minima located here or the maxima located here? The maxima or minima that is located actually varies with respect to time, correct? This is a clear case where if I consider that at some time t equal to 0 the minima is located here, at the next time instant the minima would have shifted either to the right or to the left, it does not matter where it is, but the point is it has shifted. So, this minima or the maxima will be moving along the transmission line, and therefore, they do not represent the stationary points along the transmission line, they are actually moving along the transmission line, and hence this is the case of a travelling wave. Okay. Now, before I consider other cases, let me consider another situation, okay, wherein just describing everything in terms of the reflection coefficient will not be helpful. I need to consider what is called as the transmission coefficient. Okay. The transmission coefficient is best obtained by considering this following scenario. So, I have one transmission line over here, I have some Z01 as the characteristic impedance of this transmission line. On this line I have both positive going voltage as well as negative going voltage. I terminate this transmission line with the load ZL, okay, through which some current IL can be flowing, okay, and then to the right of the load I consider a second transmission line, I connect a second transmission line of characteristic impedance Z02. So, there is now a voltage. What happens physically is that a voltage would arrive from the source, hit the load, and if ZL is different from Z01 there will be reflection, okay. So, there will be a reflected voltage. However, there will be some voltage drop across the load, and the remaining voltage would actually be propagated along the second transmission line, okay. You can also think of a current being in the same way. So, I have a current incident, current reflected, some current passing through the load, and the remaining current that is being transmitted. So, I have incident Vi, reflected voltage Vr, and transmitted voltage Vt. Please remember, Vi will be plus, Vr will be minus, Vt will again be plus. All this is happening at the load where I have kept the load at z equal to 0, and my z axis is increasing in this way. Now, I am interested in not only knowing how much the voltage is getting reflected, but also how much the voltage is actually transmitted. In order to do that, I have to write couple of equations. Those are kind of very easy to write them. From the left, if I approach the transmission line z equal to 0 from the left, then the total voltage will be Vi plus at z equal to 0 plus Vr minus at z equal to 0, correct. This is the incident plus the reflected voltage on the transmission line at z equal to 0. This should be equal to VL, but I know from KVL that whatever the voltage that will be there at VL must also be the voltage of the transmitted voltage, right, on the second line, that is on the transmitted voltage on the second line at z equal to 0, okay. From this KVL this is very clear. So, at Vt, because if you approach this load from the right hand side, that voltage will be Vt plus at z equal to 0, and that would be equal to the voltage on the load. Clearly, there is no reflection here because there are load that we have kept is kept at infinity, and it would take almost an infinite time to come back, okay. What about the current waveforms? Well, there will be current. The current will be the total current corresponding to the incident, which would be Vi plus at z equal to 0 divided by Z01 minus VR minus divided by Z01 at Z equal to 0. This is the incident current on this side. There will be some current through the load and the remaining current will be transmitted, right. So, this must be equal to the current through the load, which is IL, plus Vt plus Z equal to 0 divided by Z02. Okay. Clearly, this is the current which is incident, this is the current which is reflected, this is the current through the load, and this is the current that is transmitted. Okay. Now, you can simplify these two equations. I will not simplify them because this is mostly algebra and we do not really gain much of a physical intuition out there. But if you simplify these two equations and then find out what is the ratio of VR minus, that is the reflected voltage, at Z equal to 0 to the ratio of Vi plus at Z equal to 0, this would be the reflection coefficient for the first transmission line, or since there are only two transmission lines, it is kind of understood that this is reflection coefficient at the first transmission line. Therefore, I will remove this subscript 1, I call this as gamma L, and this gamma L is now given by ZL parallel minus Z01 by ZL parallel plus Z01. In case you are wondering what is ZL parallel, you would actually see that one if you solve the two equations previously that I mentioned. This is given by Z of the load ZL and the second transmission line Z02, ZL plus Z02. This is actually ZL parallel with Z02. Okay. Z02 is the characteristic impedance of the second transmission line, and Z01 of course the transmission line, first transmission line characteristic impedance. This is the overall reflection coefficient now. What is interesting to observe here is that the reflection coefficient does not only depend on the load ZL, but also depends on the second transmission line characteristic impedance that we connect. Okay. If I am interested on what is the amount of the voltage that is actually transmitted onto the second transmission line, I have to find out what is Vt plus at Z equal to 0 to what is the incident voltage that I have sent, and this ratio of the transmitted voltage at the load to the incident voltage at the load is called as the transmission coefficient. This is denoted by, there is not a standard number or a symbol to denote this one. I pick tau, okay. Some people pick different symbol to denote this one. So, in my language tau represents the transmission coefficient, and this value is given by 2 ZL parallel divided by ZL parallel plus Z01. Okay. You can show this again by some algebra that you would obtain by solving the previous equations. So, this is the transmission coefficient. Okay. And we will later see what would happen to this transmission coefficient, why would it be important when we consider the power that is carried away by these voltages. To briefly tell you what it means, there will be some incident power carried, okay. There will be some reflected power that is carried by the reflected voltage, this is the incident power. There will be some power that is dissipated in the load, and there would be some power that would actually be carried away by the second transmission line, in case I have the second transmission line. If not, then this would be the three powers and the total power would actually be constant. So, we will stop here and continue the solution of the transmission line in the next module. Thank you very much.